Hi. Recording.
Okay, just to introduce you, Marius. So we thank you again a lot to Professor Marius Tucsnak for accepting to give a talk in our Congress. So Marius Tucsnak is a full professor of mathematics at the University of Bordeaux in France. His fields of expertise are the analysis and control of systems governed by partial differential equations. So today his talk will be PD system describing the motion of solid in a viscous fluids, wellposedness, control, and log time behavior. So thank you very much, and you can start.
Thank you very much for the invitation to deliver a talk in this anniversary seminar. So I've been I attended this seminar, I think, a very long time ago, more than 20 years ago. So I'm happy to be back in this virtual manner. What I will discuss today concerns the mathematical description of the motion of solids, mostly rigid ones, in a viscous fluid. And the questions discussed will be the wellposedness of the coupled PDE ODE systems arising in the modeling of these systems, control theoretic questions, and more recent results on the long time behavior, which can be stated in a very simple manner, and where the interesting and the difficult part is the proof, the techniques used. The questions I will discuss are part of a broader range of problems which concern the fluid structure interactions which arise naturally in many fields of science and of engineering. I have here three examples. First three examples. The swimming of aquatic microorganisms. So this is a kind of a ciliate organism in the left picture. It's a very fascinating phenomenon, which will be discussed briefly in this talk. Then there is sedimentation processes, which at the end lead to non-Newtonian fluids, but nevertheless, initially they concern Newtonian ones. And one of the oldest problem in marine engineering, describing the motion of submarines, which are self-propelled rigid bodies moving in an ideal fluid, or at least considered mostly ideal in engineering. What's interesting for these problems? I would say that the main thing is that they involve a free boundary. More precisely, you have a fluid, which let's say occupies the blue domain in this picture, and which is described, for instance, by the Euler equations of an ideal fluid or the Navier-Stokes equation of a viscous one. Then you have ODEs, which describe the motion of the rigid bodies, which most of the time in my talk will be considered to be completely immersed in the fluid. So I have these red objects which represent the rigid solids immersed in the blue fluid. Of course, they are governed by Newton's laws, but Newton's laws would say, the main one being the second one, which says that mass time acceleration is equal to the sum of the forces acting on the solid, on each solid, and essentially these forces come from the fluid. So it will be the sum of the stress vectors exerted by the fluid on the boundary of the solid. What's interesting, as I mentioned in this situation, is that the domain, the blue domain, the domain filled by the fluid, depends on time, and it depends on time in an unknown manner, in the sense that the motion of the bodies is not considered to be a priori known. So within these lectures, it will be considered that the system is a coupled one and that the motion of the bodies determine the geometry of the fluid, whereas the motion of the bodies is determined by the forces and torques exerted by the fluid. Strangely enough, this kind of problem, which is very natural, imagine that you just throw a ball in a pool, a heavy ball in a pool. So these kind of problems, which are very natural, have been mathematically studied quite recently, especially in the situation where the fluid is described by the Navier-Stokes equations. Let's say very early result, pioneering result in this direction has bin given by Denis Serre in 1987, where he considered the case of one body which moves in the whole space. In this case, there is a simple change of variable, which in a certain sense simplifies a lot the problem, and which anyhow would fix the geometry. So it solves one of the difficulties. Sometimes it may generate other ones, but in the case considered by Denis Serre, it was essentially a simplification, which allowed him to obtain remarkable results from 1987. The case where you have more bodies or only one body, but in a bounded container, like in the picture you can see here, has been studied much more recently. So the story began around 2000 with a series of papers of Hoffman and Stavov-Voitov, then Desjardins and Esteban, and Carlos Conca, Jorge San Martin, and myself. It was first on weak solutions. So references 2, 3, and 4 considered various notions of weak solution for which existence was proved. A bit later, beginning with 2003, a theory of strong solutions began with the work of Takeo Takahashi. Well, which are the mathematical challenges we would like to present in this talk? As I mentioned, existence and uniqueness of solutions, but also control problems may appear, for instance, when we want to describe swimming. So here I will try to animate my screen. You have something which looks like a fish, and which moves in an aquarium. So you see very small motions allow, however, a quite significant displacement. This object is a robot, in fact, is a robotic fish produced somewhere in England, like 5 years ago at least. And in the second image, we have a simulated fish, which you see has more difficulties to swim. I will try to explain maybe later on why it is not so easy to describe real swimming, and I can even tell it from now. It's because it involves a very high Reynolds number. Fish-like swimming involves a huge Reynolds number, which is difficult to catch up by simulations. Other situations which will be interesting in other basic question is that the large time behavior. So if I look to the first picture with a small red ellipsoid in the blue fluid, and I imagine that the blue fluid is infinite, so it fills all the remaining part of the space. A natural question is, I just give an initial velocity in a neighborhood of a solid. And then I do nothing more. And I ask myself, what will the solid do in large time? Will it stop somewhere or asymptotically stop somewhere at finite distance? Or will it slowly slide towards infinity? So this is a kind of philosophical question to which we obtained the answer only very recently, at least in free space dimension. In two space dimension and one space dimension, the question has been discussed in previous papers. Another very fascinating example, it's at the middle, is what is called the Stirling engine. Here there is a coupling of the motion of a compressible fluid with the motion of a piston, which is a rigid body. And the motion is due to the fact that we maintain a difference of temperature between two parts of this structure. So this is what's called the Stirling engine, which is a very simple structure, which mathematically is very challenging. And finally, something I will discuss very briefly, if I really have time, at the end, which is floating structures. So here I have a double free boundary problem. There is a free boundary between the solid and the fluid, and there is a free boundary between the fluid and the air. So this is a very complicated problem on which the first results are very recent. The outline of the remaining part of the talk is as follows. I will first discuss modeling and wellposedness, then a control problem which is tractable, which is swimming at low Reynolds number. If you remember the ciliate, the microorganism, it corresponds to that situation. And finally, I will discuss long-time behavior and possibly floating structures. So what are the models involved in these problems? So quite generic ones. For the fluid, I can have Navier-Stokes or Euler, but let us say that here I have Navier-Stokes with a coefficient nu, which is a viscosity, which is strictly positive. And the Navier-Stokes equation with the condition of free incompressibility condition divergence of V equal to 0 holds in a domain denoted by f of h of t, where h of t is the position at instant t of the center of a rigid ball, which moves in the fluid. So the physical situation here is I have a container, capital omega, which has this croissant shape. Inside, I have fluid, and inside the fluid, I have a rigid ball of center h of t and say of radius 1. And then the domain filled by the fluid denoted by f of h of t is determined only by the position of the solid. That's why it is denoted by f of h of t, and that's where the Navier-Stokes equation holds. Then I have an interface between the solid and the fluid where I have the continuity of the velocity flow. So this is a version of the no-slip condition. So what is the notation here? As I mentioned, h is the position of the mass center of the solid, h dot is the velocity of its same mass center, and omega is the angular velocity of the solid, which in 2D will be a scalar. In 3D here, I should write a vector omega cross product x minus h. So here in the right-hand side of the fourth formula, I have nothing else but the rigid velocity field. Then I have the balance of linear and angular momentum for the solid. So mass times acceleration of the solid is equal to the sum of the stress vectors, sigma of V and P, is the stress tensor in the fluid. So I integrate the stress vector sigma applied to N on the boundary of the solid, and I obtain the resultant force. Similarly, if I integrate x minus h orthogonal times sigma n on the boundary of the solid, I get the resulting torque. So the before last relation is nothing else but the balance of angular momentum. So this is a complete system of equations describing the motion of a single rigid body, rigid ball here for simplicity, in a solid. And as you see, you have this coupling. F, the fluid domain, depends on h of t, but h of t via, let's say, the fourth equation depends on the velocity field of the fluid. These type of models can be complicated. We can add the temperature in the thermal effects in the fluid. We can take more than one solid, but the type of equation is quite similar. This doesn't mean at all that the mathematics behind will be similar, but at least the models will be pretty similar. Now, what is the solution? Due to the fact that the boundary is moving in an unknown manner, we have to define this carefully. Things are easier for strong solutions, which I define on this slide. So the idea is that you can construct quite easily whatever the position of this ball is. Here is the initial position. If my ball is, for instance, here, I can map the corresponding fluid domain on the fluid domain corresponding to the initial position of the ball. And this change of variable, I denote it by capital X. And then I say that a vector field V, which corresponds to a velocity of the fluid, has a certain regularity if composed to this capital X, it has the corresponding regularity. So here is a formal definition of strong solution. So it's L2 of H2 for the velocity of the fluid, but it means that it's L2 of H2 when I compose with this, let's say, a change of variables, capital X, which should have some extra properties. We will come back to that later. But in order just to define solution, the smoothness of capital X is enough. And then, of course, we have to show that this definition does not depend on the choice of capital X, and this is not a difficult issue. So within these definitions, the equations which we see here are satisfied almost everywhere in X and in T. So all the terms which I see, for instance, in the Navier-Stokes equation will be in L2. So it's the same situation as for Navier-Stokes equations. For people closer to numerical mathematics, what I have described here, maybe recall them what's called ALE formulation, arbitrary Lagrangian Eulerian formulation, where in order to solve numerically this kind of equations, the variable domain is mapped on a fixed one, and this mapping can change during the integration process in function of time. And also, maybe what I have described recalls to some of you the Lagrangian description of the fluid mechanics, in which capital X is nothing else but the mapping defined by the flow lines of the fluid, which is indeed a solution. In other words, it is the integral curves, capital X is defined by solving the initial value problem for each small y, which is written here, and which define the fluid trajectory. So it's a possibility, but which is not the most practical one to do analysis, because let's say its smoothness depends. The smoothness of capital X would depend on the smoothness of the velocity of the fluid. The change of variables we will see later on depend only on the motion of the solid, which is much smoother. So that's a point which technically is important. So once again, capital X, the change of variable, can be defined by the flow lines, but by the flow, but more convenient choices are generally done both for numerics in arbitrary Lagrangian Eulerian and or for analysis of these problems, which is one of our subjects. So for some references for strong solutions. So as you see, the story began with a paper of Grammont and Madé in 2000, where there were some very restrictive assumptions. And then all this has been a lot improved. And mostly in a Hilbert space setting. And there is also a work more recent, relatively more recent, of Geisser, Goetze, and Eber, which consider an LP theory. This LP theory has been improved in a recent paper with Hervedosa and MIT, which I will discuss a bit later. Okay, so I said that the change of variables, which consists just in following the streamlines, is not the best one, or at least does not seem the most convenient one. So let me describe the one which we have used. One of the things which is convenient is to construct a change of variables which preserves the free divergence condition. To this aim, we do the following things. We construct an artificial velocity field denoted by Z, which is free diversion outside the solid. So here it's in 2D, which is 0 on the exterior boundary, if any, and which has some nice regularity properties. Once we have done this, we construct the flow associated to this artificial velocity field, which is not the velocity field of the fluid. So we obtain in this way a change of variables capital X, which has the nice property of preserving the free divergence condition. Maybe not yet, not yet. To make it preserve, we multiply by the cofactor matrix of the Jacobian of the inverse mapping capital Y. And then, in fact, we have obtained in this way a new velocity field, capital U, and a new pressure field P. And moreover, before doing this, I should have said this change of variable capital X is slightly modified by truncation. So it will be identity far from the obstacle, and it will coincide with the motion of the obstacle in a neighborhood of this one, so in this black region. So our change of variables is a change of variables which follows the obstacle in the black region, which does nothing when you are far from the obstacle, which is the identity, and which has a property of preserving the volume, the elementary volume everywhere. So it's a bit technical to construct that, but it's still extremely elementary. Once we have done this, our system becomes a system written in a fixed domain, still with free divergence, but with much more complicated operators, L instead of the Laplacian, N instead of the nonlinear term, an extra term mu, which comes just from the change of variable. So Navier-Stokes equation becomes a more complicated one, where the operators M, L, N, G depend on capital H and on the angle theta. Nevertheless, these operators, for instance, L, will be close to the Laplacian when time is small, and exploiting this and some maximal regularity for parabolic equations, we are able to prove existence and uniqueness of strong solutions for this kind of problem. So first, using a linearized problem, which is still a coupled one, this is an important point in our approach, and then using maximal regularity and a fixed point, the procedure. So this is, I will say nothing about weak solutions. There is a different literature on that, which is a bit older. The problem was understood much earlier, at least partially, for weak solutions. The more recent developments concern strong ones. So now, just some words about fish-like swimming. You will be astonished, the fish is not a rigid body, indeed. But the usual way to model it is to say that it's an object which deforms according to a prescribed given law. So the deformation is given and is like a control functions, whereas the rigid displacement will be computed. So there are some conditions called of self-propelling here, which I don't detail. It's H3 and H4. They, roughly speaking, say that you should not speak about swimming when you push the object with an exterior force. It should come from its own deformation, and these are conditions H3 and H4. And with this, the model is quite similar to the rigid bodies. So we don't have equations of elasticity here. We just have the rigid body motion. And the only difference with respect to the rigid body case is the presence of this W, which is, let's say, the deformation velocity of the fluid, of the solid, which can be seen as an input function. It's a bit more complicated than that, but a simplified way of seeing it, it's this. So, in fact, the system is very close to the system describing interaction of rigid bodies and fluids. For these ones, the Fujita-Kato type approach, which we have developed in a series of papers, applies very well, and there are some papers published more than 10 years ago, which from a theoretical viewpoint allow us to construct strong solutions which are global in 2D, and of course global only for small data in 3D. To get a control problem, so fish-like swimming is something which happens at high Reynolds. It's something which is like here in this movie, which has been done by G.I. Taylor. So a very simple robotic fish is just an elastica and a flip-flap cue. This object put into water will swim, as you will see soon. It's maybe a bit too long, I'm sorry. So it goes down, but you see that it swims. Now the same thing when in the same object in a fluid with a lot of syrup in it. It will not advance. What it wins at one, in one sense, it will lose the opposite on the opposite one. So the two systems differ by the Reynolds number. So here we have a control problem in which the geometry is the input. And in fact, it turns out that after some work, which I will try to skip, we obtain with a lot of assumptions a problem which is writes like here, which is an ODE, because in the fluid, we consider that at each moment, we have a stationary Stokes equation. That's how we translate low Reynolds number motion. And then I don't have evolution equations for the fluid. I have them only for the solid. And then I can write an ODE, but which is abstract because there are some solution operators here of Stokes equations, which are not known in general. But one should know that what we get, so C is the position of the mass center, R is the rotation matrix. Here we are in 3D. And then we obtain an ODE system. And what we have seen in the movie is the theorem of Purcell, called scallop theorem, which says that if the deformation is something reciprocal, as you have seen, the body will not advance. So that's a rigorous theorem which can be proved. And then we have looked to other situations, which I will not detail, to ciliate organisms, like here. So this is the rigid ball where it has many hair-like small organs on the boundary, which you cannot see. And we computed some time optimal control. You see a funny way of advancing. It's pushing laterally the fluid to advance. Of course, it's not completely symmetric with respect to the horizontal axis, because otherwise we do not advance. But you see that a very interesting method is pushing the others to go quicker. I will end up with long time behavior. So as I mentioned, you can ask this in several situations. So I will ask it in this one. I will discuss only this one. I just take the rigid ball and I give it an initial impulse, and I'm waiting to see what will it be doing in long time. So the equation are exactly those we have seen. My fluid is now unbounded. So I have a ball, let's say, and the fluid domain is R3 with the exception of this ball. So the equations, I don't repeat them, they are here. And what we obtain for small data, I first remind to you the existing results. If the domain is bounded and the data are small, then there is exponential decay of the velocity of the solid included, which means that it will asymptotically stop somewhere. In 2D, in unbounded domain, so if the fluid solid domain is whole of R2, we don't know. There is a result of Hervedosa, Hileret, and Lacave, which says that the velocity is bounded by 1 over square root of t. But this doesn't say if it stops or not, because if you integrate 1 over square root of t, you get 2 square root of t, which goes to infinity. But since this is just an upper bound, you don't know. And nothing was known up until recently in the case when omega is all R3. And here we have our results with Hervedosa and MIT, with two versions, one for rigid balls, one for arbitrary shapes, where we essentially prove that the velocity behaves a large time like 1 over t power 3 over 2, which means when I integrate with respect to time, that my solid will stop in finite time. Saying where is another philosophical question to which I have no hint. So, just one word, it's based on change of variables, linearization, and then some quite delicate resolvent estimates, which I will not describe here, and which go back to Iwashita in the case of the Stokes equations. So here there are some references, and maybe the main message I want to pass is that in all these coupled problems, we linearized, but we never uncoupled. Our linear problems are still coupled, so we had to study a new operator, which we call fluid structure operator, and which has many common properties with the Stokes operator, but each time they have to be proved, and it's sometimes a quite delicate work. I think I will end here, and I'm of course open to questions.
Okay, thank you very much, Marius, for this very nice talk. So let's ask the audience if they have some questions or comments. Please use your microphones. I think they are available. Yes, audio is opened. So please go ahead. So while people thinking, so I just wanted some curiosity. Do you have some result for non-homogeneous fluid where with variable density?
I don't have, but there exist such results. So the original results on weak solutions have been done for non-homogeneous fluids. For strong solutions, I don't know, but for weak solutions, there are results which apply to non-homogeneous fluids. Yes.
Okay. Okay. And the author, do you remember who are the author of such results?
Yes, it was in particular Starovoitov. So my one of the authors is Starovoitov, and the other one may be Plodnikov, but certainly Starovoitov has papers on that.
The Russians, no?
I will give you the reference. Yeah, I don't know by heart, but Starovoitov, and they are quite old. They are from the beginning of the 2000s.
Okay. Okay. So
Since then, certainly other people have been working. I think essentially, even for strong solution, there is not a big difficulty, but I would be careful because there is a transport equation which comes there, and it may be, yeah. So there are results. On the contrary, we have recent results, including mine, on compressible fluids. So where there is also a transport equation. So for compressible fluids, the theory of strong solutions is quite well understood.
Okay.
So these are results of me and my team 2 or 3 years ago.
Okay, thank you. Other questions?
I have one question.
Okay.
It's also a curiosity. Marius, is there any result when do you take the viscosity to zero? Some
Yes.
Venture viscosity result?
Yes, at least one. So historically, the first one in this direction is the result of Takahashi and Rosier, where in fact they pass the viscosity to zero to obtain an existence theorem when the solid is ideal. So the first result on existence with an ideal solid is obtained exactly by this method. But of course, in order to do that, they have to change the no-slip condition, and somehow let's say, formulate a new viscous problem, which they study, and then by passing to the limit, they obtain the Euler equations.
And it is a kind of Navier boundary conditions?
It's a kind of Navier, but it's at the interface.
At the interface, okay.
The interface, so it's a kind of Navier boundary condition, yeah. So they should, on the interface, not put the condition which you see here, but a more complicated one on the boundary of B.
Okay, is a result by Takahashi and
Rosier.
Rosier, okay.
Which is one of our speakers, no, I think, yeah.
Yeah.
I think it's very old paper.
Okay, okay.
Very old
have
paper.
a look. And I guess that the same holds for Burgess, no? For 1D model. When you pass, you have...
Oh, for 1D, what do you mean? To pass with the viscosity to zero?
Yes, when you have a
I'm not
particle.
sure that anybody did that, but I think so, but I have no references on that. Yeah.
Okay.
On burgers, the original papers on this type of models some of the original papers were by Zuazua and Vasquez,
In Vasquez.
where they looked at the long time behavior.
Yeah.
And in 1D, it will go to infinity, the body. I should have mentioned also this. Where they prove that the point, but 1D burgers with a point mass is not really a realistic model for our problem, because there is no free divergence, of course. You cannot keep the free divergence with burgers, so it's a slightly different question, but I think that passing with the viscosity to 0 is completely possible, yes.
Okay. Thank you very much.
Okay,
Welcome.
thank you, Diego. Are there other questions? So if not, Marius, thank you very much for your talk and for being with us. So we finished the morning